In this video, we're going to be using some calculus to help us figure out the velocities, accelerations, and positions in situations where we do not have just a constant acceleration. So previously, we've learned using this idea of constant acceleration how to find certain kinematic equations of motion for an object experiencing a constant acceleration. And we did this process whereby looking at the velocity graph, we were able to say, okay, well, the slope of this graph is going to be the acceleration. And that was easy to do when we have a linear relationship and velocity is directly proportional to the time. Well, the slope we can just do rise over run, and that just gets us a constant number, so constant acceleration. And going the other way, if we found the area under this curve, that area under the curve ended up being proportional to the time squared, giving us a quadratic relationship between position and time. Also, way back when we did our lab in this situation, we found using the graphing analysis software, we were able to find these different instantaneous slopes, which we used to construct this velocity graph. So one of the things we're going to look at today is, well, how were we able to find these instantaneous slopes from this graph? How are we able to find the velocity at each of these points when it is not a linear relationship, when we cannot just do rise over run? So good old Isaac Newton is going to help us figure that out. So I'm going to walk you through his method. We'll be finding something called the derivative of a function. And I could write, let's say I'm looking here at this position versus time graph. And let's say this is some form of, we'll be doing polynomials. So let's say it's the position is related to some m. This is just going to be some constant times t to some power. And this we'll say is an integer. So this is a polynomial, right? This could be, I don't know, 5t squared or negative 2t to the fourth, some polynomial function here. And I want to be able to find out what's the velocity at any point in time here. I want a function that can tell me what is the velocity here at this time, which would be the slope of the tangent line at that location. What's the velocity here at this point, and so on. How can I find those things out? And finding the derivative, and the derivative just is a word for finding the rate of change of position over time at each of those points. And the way I rate that is I'm looking for the velocity, right, which we're going to call the derivative of the position with respect to time. So the way I write that is going to be dx dt. You can sort of think of these d's standing for delta, right? Position, change in position over change in time. Well, that's velocity. So that's our symbol for the derivative. By the way, if anything I say here contradicts something your math teacher says, well, there's a reason that they're teaching math and not physics. Just kidding. Go with whatever your math teacher says. They're probably much more educated on how to teach this than I am. All right, well, let's get to this. Let's say I'm looking at, I want to find at this, well, let's say anywhere. I want to find the slope, the derivative, the rate of change at any point here. I can't just do rise over run because let's say I'm looking here. If I were to just do some sort of rise over run, maybe from the start to that point, well, that slope is obviously different than the actual slope at that point. So that's an issue, because that's how I know how to find slope. I know how to do rise over run. So we want to figure out a way, how can I do rise over run, but have it match up with the actual slope? And the way we can do that is we can think, well, all right, these 2 points were really far away from each other, and that gave me a very different slope than at this point. What if instead, I picked 2 points that were closer together, this point and this point? Well, that's a little bit better, right, compared to this. We've gotten a little bit closer to the actual slope at either of those 2 points, but it's still not very good. So okay, what if we pick 2 points that were even closer to each other? Well, yeah, this slope is again looking much closer than this one. And okay, let's keep continuing that process. What if I do these 2 points that are really close together? And you can see that slope is even closer to the tangent line at that point. So the idea of taking a derivative is just trying to get 2 points getting closer and closer. I'll do this point and this point here, and that slope is going to be very close to the slope at just that one point. So the idea is if we can get close enough, if we can get infinitesimally close, 2 points that are right next to each other, then we found if the slope, we can find the slope between those 2 points, and that's basically going to be the slope at one of those points. So let's look at how can we do that. So let's just find 2 points in time. So I'm going to find 1 point in time. I'm not going to draw these right next to each other because then it's going to be hard to see. We're going to have our time. And I'm going to also find a time that's just a little bit more, a little bit further ahead. And I'm going to call that our time plus a little bit that I'm going to call h. So I've added h, and h is going to be some very small number. And each of these points I could find the velocity. Not the velocity, sorry, the position at each of those points. So this has a position, whatever my equation is, right? So my position is some function of time, so this would be x of t. I just plug that into whatever equation I have for the position. And this one would be x of t plus h. So I could just plug those into my position equation. Now the slope between these two, which is going to be similar to, but not quite the slope at either one, would be my rise over my run. So my delta x over my delta t. So let's write that out. My velocity is going to be equal to my delta x over my delta t. All right, now let's substitute in. We know delta means final minus initial. So let's do that. So we got our final position, which is the position at time t plus h, minus the position at time t, divided by our final time, which was t plus h, minus our initial time, which is just t. That's going to be our velocity. Again, your math teachers can use some more in-depth knowledge about all this, but this is the general idea. So we're doing rise over run. Now the idea is to get these points as close together as possible, because that will give us the most accurate measurement of the slope at just one point. So what I want to do to get these as close to as possible is I want to make h as small as I can. The smaller h is, the more accurate this line will be for my slope. So what I'm going to do is I'm going to take the limit. And you've learned about limits in your pre-calc class. I'm going to take the limit as h goes to 0. At both these sides. Because what that's doing is it's saying, okay, these things are some distance away, but I'm going to bring them as close as I can. I'm going to make h so small that these 2 points are almost on top of each other. And that can tell me the slope, basically, at just that one point. And this is as far as we can get without actually putting in some function for x. So this would have worked for any sort of function up to this point. It wouldn't have to be a polynomial or anything. From here on out, we're going to say, okay, the case we're looking at is when position is a polynomial function here, some mt to the n. So let's plug in as a polynomial function for our positions here. So we got our limit. Let's do h in a different color so we can sort of keep track of it. As h goes to 0, let's put in our polynomial function. So we have m t to the n. So here it's t plus h to the n, because that's what my x variable is here, minus m t to the n, because then I'm just plugging in each of these into the t spot here. And then I can cancel some things on the bottom here, right? I got t plus h minus t. Well, that gets rid of the t's. T minus t is 0. All right, so we put all of this over just h. Now we're going to do a little bit of algebra. So I can pull the m's out. They're not really relevant. So limit m. I'm going to leave it over h, so we'll see why in a little bit. H t plus h to the n minus t to the n. I did say we'd keep these a different color. And now I want a way to try to simplify this a little bit, because I have this issue right now where, if I take the limit as h goes to 0, well, this might give me something undefined, right? Because I got a 0 on the bottom, something over 0 is a undefined solution. So let's try to see if there's anything we can do to this top part. And we could write out this guy right here, right? So some math real quick before we do that. If I have x plus y to some variable, well, that's going to be x to the n plus n times, plus n times x to the n minus 1 times y plus a bunch of other stuff. And you can see that if I do, let's say a squared, really, x plus y squared we know is x squared plus 2xy plus y squared. Let's see, I threw in I did it cubed, so that would be x plus y cubed. Well, that's just this times x plus y again, so I get x to the third plus 2x squared y plus x y squared. A little quick here, let's fix that up a little bit. So that's all those things times x plus x squared y plus 2xy squared plus y cubed. And that's a little messy. We can combine some of these terms and we get x cubed plus 3x squared y, because I had 2x squared y and x squared y here. And then plus a bunch of other stuff, which it turns out we're not going to really care about. Do note that all this extra other stuff has y squared or more terms in it. That's going to be important. All right, so I can write that in here. Got my limit, still have my m. And I've got, instead of y, this is t plus h instead of x and y. So it's going to be t to the n plus n t to the n minus 1 times h plus a bunch of other stuff. That's all multiplied by h. minus t to the n all over h. It says h goes to 0. Okay, so I can cancel now. I have t to the n here, plus a bunch of other stuff, and then I'm subtracting t to the n. So I can get rid of these. And when I do that, I end up with a bunch of terms, and t to the n minus 1 h plus a bunch of stuff that's also multiplied by h squared and h to the third and so on. So I'm not going to write out what each of these are. H squared plus something, h to the third, yada, 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 over h. And again, I messed up here. We should be having these all be different color. All right. And hey, all these at least have one h in them. So I can cancel this h in the bottom with one of the h's on the top. That's going to get us our last expression here. So I have n t to the n minus 1 plus some stuff times h plus some other stuff times h squared and so on. And my limit has now become pretty easy to do. Well, as h goes to 0, I don't have anything in the denominator anymore. I don't have to worry about any weird stuff happening. This goes to 0. And this goes to 0 because they're multiplied by h squared, and so on. And there are more terms here. So these all go away when I take this limit, which leaves me with just this first term. N t to the n minus 1. Let's add another page here. What was all that we were solving for again? Well, we were trying to find the velocity, the slope at that point. So it turns out the slope for a polynomial of order n equates, we left out this is all multiplied by m. So let's just throw that in there, to this value. So let's just write those next to each other just so we don't get lost. We had m t to the n. And it turns out when we found the velocity, which is the derivative of position with respect to time, that's the process we did, it ended up being mn t to the n minus 1. All right, so now we have a process for finding the velocity from a position graph of any sort of polynomial. It doesn't have to be a t squared, it could be a t cubed, t to the fourth, t to the negative 2. We now have a way to find the velocity function. And then we can use a similar process to do the acceleration. Just as velocity was the rate and change of position over time, acceleration is the rate of change of velocity over time. So I could do the same process I did with this. I could do that here onto this function to find its derivative, which would be my acceleration. Let's look at an example. I'm going to have some position versus time, and I'm just going to graph it, because why not? Let's say it's a t to the fourth relationship. Let's say it's 5t to the fourth. So the position, and I should have units in here, but we're going to skip that. Position is 5t to the fourth, and I want to make a velocity graph. So I have 5 for my m, and n is going to be 4. So let's see what I have to do. I have to multiply this down. So I'm going to do 5 times 4. Then I'm going to subtract 1 from the exponent. So basically, I'm just subtracting 1 from the exponent and multiplying everything by the original exponent. We can see that's what's happening here. So 4 times 5 is 20. So I've done this first bit here. And then 4 minus 1 is 3. So it's going to be 20t cubed. And well, that also just sort of looks like this. I'm just graphing it qualitatively. So there we have it. Finding the velocity using the derivative. And acceleration, we would then find the derivative, the rate of change of this. So how is my velocity changing over time? So let's do the same process. Here, my m is 20, and my n is 3. So bring that 3 down, 3 times 20, 60, and then 3 minus 1 is 2. So a equals 60t squared. And again, that just looks like some sort of curve up. All right, now what if I have, where did this come from? What if I had a function that was multiple polynomials? Let's say it was, some m t to the n plus a t to the b. Well, I could just do these individually. I could find the derivative of this and then just add it to the derivative of this one. So that's how I can do those things like this. Your math class will talk more about why that works out. All right, so here's a little practice. I've got 4 different functions of position with respect to time. So this one's just a constant position. Here we have a quadratic relationship like we've seen before. Here's a quadratic with a starting position. And here's a little bit more complicated of a combination of polynomials there. Try to figure out the velocity with respect to time, acceleration with respect to time, make a graph for each one. And as a bonus, note any intercepts and inflection points that you see on those graphs, and we can look at why those are important. So I would pause the video, try this out, then you can hit play again, and I'm going to go through each of these. All right, so the first one. And I look at this and say, this isn't a polynomial. This is just a constant. Well, yes, but I could write it as 4 meters times t to the 0. Or I could just say, well, Mr. Vogt, I already know that when I have a constant position, I'm not changing my position over time. I know my velocity is going to be 0. So you could shortcut that. But if you look at this with our equation, well, if I bring the 0 down, I'm multiplying everything by 0. So it becomes 0. So that checks out either way. So velocity and time is just going to be a line at the 0. And acceleration by the same reasoning. Well, my velocity is not changing with time, so my acceleration is not changing with time either. Intercepts and inflection points, it's all 0 because this one's not changing, therefore this isn't changing, therefore that's not changing. All right, a little bit more complicated. Now a common mistake might be to look in this and say, oh, I know from my kinematic equations that 6 meters per second squared, that's the units of acceleration. The acceleration must be 6. And that wouldn't exactly work out for you. So be careful about relying just on unit analysis here. Let's go through it and see what the real case is. All right, so velocity, using my equation, which hopefully you have written down, so I have to go up to it. I bring this 2 down, 2 times 6 is 12. And then t squared, that 2 minus 1 becomes just t. Meters per second squared. Keep the units. All right, cool. And what does that look like? Well, that's linear. Yes, this is the constant acceleration case. So we'll notice some things. No velocity at t equals 0, which makes sense looking back at our position graph. Right here, the slope is 0, and it's becoming more and more positive. No inflection points there. Acceleration and time. Again, now we're going to take the derivative of the velocity with respect to time. So this I could write as t to the first. So 1 times 12 is 12. Keep the units. 1 minus 1 is 0. T to the 0. And t to the 0, well, that's just 1. So here I have a constant acceleration, 12 meters per second. Again, this is one we could have done before, just saying, okay, the slope of this line is 12 meters per second squared. So the acceleration needs to be a constant 12 meters per second squared. All right, this one looks very similar, except we've added this 4 meters to our equation here. So these are identical motions, but maybe starting at a different spot. Or maybe I've just redefined my coordinate axis. So this object no longer starts at the origin, it starts somewhere in the positive direction from the origin, but moves the exact same way. And it's going to turn out, I'm just going to copy this down here. And if you did this and got the exact same thing, you'd be right. Because as we know, when we're looking at the slope, it doesn't matter where my starting location was. All that matters is the slope, and the slope of these graphs, I know I drew them a little bit differently here, is the same. And I can see that because if I take the derivative of this 4 meters, well, we did that before, it was 0. Velocity was 0. So here I just have 0 plus the derivative of this guy, which we found was 12. So if it makes you happy, you can say this is 0 plus that, but we can see that both of these objects, because position is arbitrary, starting position, our origin is arbitrary, have the same velocity graphs. And that then makes it quick to say same velocity graphs means we're going to have the same acceleration graphs as well. So this is a really important thing. Two velocity graphs can have different position graphs. The velocity graph does not give me information on position. It only gives me information on displacement. If I were to look anywhere, from here to here, it would be the same displacement. Final graph here. Let's do this derivative. I got squared up here for my n. So 3 times 2 is 6. And then meters per second squared. 2 minus 1 is just 1, so t to the 1 minus. Here I've got a 3, so I'm going to do 3 times 2, 6 meters per second cubed. This is the unit of the derivative of acceleration, the rate of change of acceleration, by the way. It's known as the jerk in physics. T squared, because 3 minus 1 is 2. All right, now let's get rid of this. What does that look like? That's kind of a funky looking. You can see this position graph was pretty funky looking as well. When is this 0? This is 0 when t is 1, because then I get 6 minus 6. So, and then the squared is bigger than just t, so then it gets negative because of this minus here. But before that, it's positive. It's going to be something like that. And you can see here I have a positive slope getting less positive. This would be t equals 1 right here. 0 slope getting a more negative slope. So what we have here agrees with that. So this would be 1 second, which would line up here with 1 second. And acceleration, we're just going to find the derivative of the velocity with respect to time. To do that, a g. All right, so t to the 1 times 6 is 6. And then t to the 0 is just 1, so we'll just leave it as 6 meters per second squared, minus 12, because 2 times 6, and then just t, because we lose 2 minus 1 is 1. 12 meters per second cubed, t. And looking at units, I can see again, okay, meters per second cubed times seconds is going to get me meters per second squared, which is acceleration. Okay, so this is a linear function. It starts at positive 6 and is decreasing. When t is, let's just try to keep these to scale. It's decreasing pretty fast. When t is a half a second, this is 0.5, I have 0 acceleration. And that would line up with right here. Because the slope at that point is 0. All right, cool. So that's finding the slope, finding the rate of change of either position or velocity with time using calculus, using the idea of the derivative. Next, we'll look at going the other way. So way back when we were able to find the area and use that to find position. or we could use the area under the acceleration curve to find velocity.